let's go ahead and get started. Hello, everyone. Welcome to day 3 of the Youth Global Health and Innovation Conference. It's our final day of the conference, and we're excited to finish strong with topics ranging from breakthrough innovations in microfluidics to global perceptions of mental health. We are so grateful to all of you for helping make this conference possible and bringing your enthusiasm, energy, and thirst for knowledge that made the inaugural Youth Global Health and Innovation Conference a success. My name is Meher Graywal. I'm a high school student at Interlake High School in Bellevue, Washington, and I'm the founder and director of Worth a Shot. So with that, I would like to hand it off to all our volunteers to introduce themselves. Go ahead, Brian.
Hi, everyone. My name is Brian. I'm a second-year medical student at the University of Washington. I'll pass it on to Luis.
Hello, everyone. My name is Luis Martins, and I'm a junior at Henry M. Jackson High School in Everett. I'm the head of communication and director of South America operations for Worth a Shot. I'm passionate about bridging socioeconomic gaps in healthcare and promoting mental health awareness. I'm very honored to be one of the hosts for this year's conference. Thank you.
Thanks, Louise. Now I'll hand it off to Annika. I'll hand it off to Chris.
Hi, all. I'm Chris. I'm about to be a fourth-year medical student at the University of Washington.
Thanks, Chris. And finally, off to Antonio. Actually, Antonio couldn't be here today, so that's fine. So let's get started and jump right into our first talk. Our first speaker today is joining all the way from Paris. So get ready for an awe-inspiring discussion on breakthrough innovations in microfluidics and microfabrication tools and their global health applications with Dr. Shreyansh Jain from the Pasteur Institute. Good morning, Dr. Jain. Greetings from Seattle.
Hi, good morning. So I guess I'm good to go. Cool. Okay. Okay, you can see the screen?
Yes, we can.
Okay, great. So good morning, everyone, even though it's late afternoon here. I'm Shreyansh Jain, currently a postdoctorate researcher at Institute Pasteur. And it is my pleasure to be speaking to many of the young people from high school and medical school for this conference. And again, I would like to congratulate all the young people who have organized this kind of conference with a lot of efforts. And again, thank you for inviting me for this. And I hope I'll be able to motivate some of you in your journey of research. So, so basically, the topic which I chose today is something which I have been working on in last 8 to 9 years during my PhD and my postdoctorate research. And I'll be talking mostly about the microfabrication and microfluidic tools and how we can use this to study human health and disease. So mainly the outline of my talk will be around 3 main topics. So one of them would be how we can use the microfabrication tools to study the fundamental mechanism of some developmental phenomenon. So when you are developing, your embryo is growing, there are a lot of cell movement and the cells can move collectively. And I will show one example, which is coming from my PhD research, that how we can use a minimalistic microfabricated tool to study the mechanism of how cells can move collectively. Later on, I will talk about one of the recent work, which is still hot from the laboratory. It's about a microfluidic tool. It's a novel microfluidic setup. It's a small chip in which you can recreate a tumor microenvironment. So you can recreate a tumor and you can challenge the tumor with some immune cells and see what happens during this immune cell and tumor challenge. And on the last part of my talk, I will talk about a recently developed tool in the lab by me. It's a kind of a biomimetic tool, which I use to apply forces on cells, forces on tissues or on organs. And that's something from which I'll be ending my talk. So let's go first for how we can implement microfabricated tools to study collective motions in cell. And it's one of my favorite movie. I would go with that, where you can see on the right. Let me take the pointer. Okay, so where you can see on the right, what you have is the herd of sheep going collectively from one barn or one field to the another field. But at the same side, you see a macroscopic to microscopic transition where you see the cells here, which are collectively moving from one place to another place. And you see a fantastic similarity in these two movies, yet they are so different in this scale. So this is something amazing what you can see in the nature. But the cells are something which are barely dumb compared to the sheep who are intelligent, who can see, feel, and move around. But then there are some more examples, and I will talk how cells can exhibit this kind of phenomenal migration. So what you see here in this movie, so in the process of development and morphogenesis, when the organs are being developed, so you see an amazing picture of collective motion. So this is an organoid from breast epithelial cells. It has been cultured inside the lab. And when these organoids grow, they assemble into these clusters, and then these clusters rotate. And it is believed that these clusters and rotating clusters are important to form lumen. And these lumens are something which transport milk in the future, you know, to the baby. So this is something which is a very interesting and a beautiful example of how collective motions happened in the process of development. But at the same side, in some pathologies like wound healing, whenever you get a wound, your wound heals over course of few days, and it completely seals the barrier. So it's something in those places, the collective migration of cells, it is very important. And you can see that the cells here collectively migrate and close this gap. So as you can imagine that this kind of process could be very important in both these scenarios. But then, as I mentioned, that sheep could be intelligent, but how cells can do that? How cells feel each other to go collectively? So basically what happens, and it's a very fundamental knowledge to some of the high school students, probably med school students know this already, that cells have cell-cell junctions present in them. And these are cadherines. So these cadherine-based junctions are connecting one cell with the other cell. And then when a cell moves, they can pull on the other cell using these junctions. So this is how cells can communicate to each other physically with the help of this protein, which is gluing one cell to the other cell. And let's see how we can recreate this kind of collective motion, which I've showed you before, using microfabrication method. So what we do here is something very simple. So what I'm showing you here is something that how you create a minimalistic system to study this kind of phenomenon. So what you see here is a silicon wafer. So it looks like something like this. The wafer is coated with a photoresist. Imagine it's just a chemical which is light sensitive. So when it's coated with a photoresist, you shine a light in a specific pattern, and wherever the light falls, those part of the photoresist convert into oxides. These oxides can be washed away by acid, and what you are left is something like these pillars. So what you can do is you can pour a PDMS, which is an elastic gel. You can pour on it, you can cure it, like you put some heat, this will become solid. You remove this PDMS and it becomes like this. So this will be your mold. And don't worry, I can imagine that some of you might be feeling lost, but think about your kitchen and the cake. If you have to make a cake, you take a mold. Let's say you want to make a heart-shaped cake. You take a mold of heart shape, you pour some batter inside that, you cook it in the oven, and you take out the cake and your cake is ready. It's something exactly similar. Your PDMS gel is your batter in this case. So once it's ready, it's time to put some protein of interest. So you put some, I say it ink, but it could be any protein of your interest. If you guys know, there is a protein or the class of protein, it's called ECM. It's extracellular matrix on which cells can preferentially go and adhere. So you can put that protein here, and once it dries out, you can reverse it and just transfer this protein on a desired surface. And the PDMS stamp can look like this. And you could put some protein transfer it, and you will get these lines on the surface where you want to put the cells. Even now, if some of you are lost, think about your school when you go to the administration to get a seal on your paper. So what they do is they put some ink on the stamp, and then they transfer that ink on your paper. So this is exactly how the protein is transferred on your surface. It could be a glass slide, it could be a small petri dish in the lab. Now let's see what we can do with this. So what you can have is ECM protein, which is a fibronectin here, which I've used, and I want to make a ring out of it. So I stamp a ring with it, I put some cells on it, and it looks like this. And so these are epithelial cells coming from dog's kidney. So these are immortalized cells, can be used as a model to study collective migration. Now what you see here is these cells which are deposited in this ring form, they expand, connect to each other, and then they start to rotate. Let me show you this movie again. So these cells are rotating. First, they kind of touch each other, and then they start communicating with each other by pushing each other, and then all of a sudden, all cells decide to go in one direction. So you can see this process is very robust. Cells can decide the direction and can go collectively. You can do some quantifications to tell that, okay, it's going in anti-clockwise direction or clockwise direction. I would not go into the detail. The movie is already qualitatively very clear to see that how the rotation happens. One of the beautiful aspects of miniaturizing this kind of biological phenomenon using microfluidics or microfabrication is you can get hundreds of such phenomena. So you can get hundreds of these just in the size of your thumb, or even half the size of your nail. You can get hundreds of such rings, and you can study all these rings to see how the coordination is happening. So that's one of the positive aspects of using miniaturized systems. And now what you can do with it is you can play with different shapes, different size, different length scales, and you can see that this process of collective migration is very robust. Think about it, like if it is not so robust, you will not get an efficient healing when you get a wound, or you will not even get an efficient development when you are starting from the embryonic stage and when you develop further. This process has to be very robust. And this is a demonstration of it. Like you change the size, change the thickness, change the length, give very sharp ends, and this process can still happen. Okay. So now how we can use this to kind of visualize some of the healthy versus disease phenotype. So as I mentioned, that cells can communicate with each other using this junction proteins. And here it's E-catherines. So you can see it is present in a dark green line, one cell to the other cell. So these all cells are communicating with this E-catherine labeled in green. You can see that the system can rotate. But what happens in some disease state, like for example, in cancer, these cell-cell adhesion proteins, their levels can go down, or sometimes they can completely disappear in the advanced stages of the cancer, where cells lose the coordination. And using this miniaturized system, you can see that in these cases where the cell-cell junctions become weak, or let me play this movie again if I could, or they completely fail to coordinate. So you can use this miniaturized system to study certain aspect of normal versus or healthy versus disease phenotype of the tissues. As you see, it fails to rotate. And not only for studying the cell migration, but you can also study certain aspects of disease like cancer, where you know that when cancer starts to grow, it applies a lot of growth pressure on the healthy tissues surrounding in its surrounding, and it can completely overtake the healthy tissues. And what you can also do is to study using this microfabrication tool to see this kind of phenomenon. So what you can have is you can print now this kind of pattern where you have a reservoir here with cell type A, reservoir here with cell type B, and you can let these cells to migrate towards each other through these channels, and you can see what happens. So what you see in this movie is cancer cells are from the top, they are coming down. Healthy cells are here on the bottom, they are going up. They meet at a particular place, and then they apply forces on each other. Let's see it in detail. What happens when they meet? So the place where you see these white arrows is the place where these two different cells will meet, cancer cells versus healthy cells. And you will see what happens after that. So over a few hours, what you observe is even though the cancer cells and healthy cells have met at this point, but then cancer cells have completely overtaken the healthy cells and they have pushed the healthy cells back. And this is how exactly happens in the case of in physiological case, when tumor is growing, it's pressing upon the healthy cells, and eventually it has a lot of other pathological consequences. So these are few examples of how you can study some interesting phenomenon of human health versus some disease phenotypes using these microfabricated tools. But now let me give you a taste of another aspect. Again, I will touch up a bit upon the aspect of cancer, but this is very, very beautiful. And let's see what kind of microfluidic pattern we have invented in the lab to study this immuno challenge to the tumors. So what you see here is a small microfluidic chip. As you can see, this small piece of Lego. So it's you can see the size. It's just a small standard glass slide, and then you have a PDMS-based microfluidic channel, which kind of hosts this entire ecosystem. I'll explain more about this movie, so don't worry. So why we are studying this, or why we wanted to study this? So what happens is, in the case of cancer, what happens is initially your immune cells try to reduce it or try to attack these cancer cells and reduce the cancer cell numbers. But I mean, eventually you can imagine that why a natural immune system can never fight it, because cancer mutates very fast. And when it keeps on mutating, at one point, the immune cell lose the check to control the cancer cell growth. And that's where it's important, you know, to kind of study how the immune cell dynamics reduces the cancer cells. So this is a histological image where you see in the brown are the melanoma, which is the skin cancer cells. And in this light purple are the immune cells. And you can see that all the immune cells are surrounding this this tumor or the cancer cells. Now, clinically, what clinicians say that if you find more immune cells in the cancer microenvironment or around the cancer, it's prognostic of a good immunotherapy. It's prognostic of a good immune sign that immune system is working well in order to reduce the cancer cells in the tissue. But then what is important is nobody knows what is the dynamics, like how immune cells come to the cancer cells. Once they reach to the cancer cells, how they kill cancer cells. People have studied, tried to study this using mouse models, but then in mouse models, it is very hard to image them. So there is this limitation in the space and in the time until which you can image a mouse to study this kind of phenomenon. And also inside the lab, you don't have nice miniaturized tools, as I've shown you before, to study this kind of phenomenon. We took it as a challenge. We developed an organ-on-chip platform where we can mimic this immuno-oncological event. And what we did, as you can see here, is a small chip. What we did is we use the droplet-based microfluidics method. So what here we do is we have oil, and in that oil, we generate droplets of liquid media with cancer cells inside this. So you can see these droplets are coming. There are some cancer cells inside. These droplets are taken further through these guiding rails, as you can see where we are moving in the device. And these droplets are taken further. And then we bring these droplets to a holding area. It's like a holding bay. Imagine a car parking, you know. And this is like a holes in which these droplets fall down, and then they are trapped. So this is our observation region. So you generate the droplet, you trap them in this region, and there you can observe them for a few days and see what happens. Interestingly, what we see is over a course of one day, all these cancer cells, they come together and self-assemble into microtumors. As you can see, we don't have 1, 2, or 10, but we have hundreds of such droplets. Each droplet has a small microtumor inside it. And you can see here that you have this small microtumor inside, and we are ready to do the next step, you know. So now you would ask that, okay, you have assembled cancer cells into a microtumor. Now how you will introduce immune cells inside it? But before I go further, let me tell you the ingredients of my research here. So what I use is B16 cell lines, and cell lines are something which are used a lot in the lab to mimic close to what a real cancer in melanoma would look like. These are called B16 cells. They are presenting a specific antigen. And when this antigen is recognized by an immune cell, it starts to attack. Okay, so this antigen is called ovalbumin. So antigen is being expressed on these cancer cells, and we call it B16 OVA. So all these cancer cells are expressing this specific antigen on the surface. Okay, now to mimic a ECM or a surrounding structure, we put matrigel. So matrigel is a kind of structural support to these cancer cells, and on that your immune cells can migrate and reach to this little tumor. So this is one ingredient. So what we do next to introduce the immune cell is, you can see these little triangular traps. So we can now bring a secondary droplet, and we can trap this secondary droplet next to this big droplet. You can see this now, there are two droplets trapped here. So one is this small droplet, like here, one is this big droplet. Now the next part would be to fuse this droplet. So don't worry, like this thing is already published, so you can see how the fusion is done. We play around the chemistry of the surface tension, and you can fuse these droplets into two. Now in the second droplet, what we bring are the immune cells, and we bring T cells here. So these T cells are already trained against this specific antigen which is present outside the cancer cells. And that's why these immune cells are already trained to kill these cancer cells. And we want to study the dynamics. So we make sure that once they are there, they can kill it. But we want to see how they reach there. So this is the important part. We call them as CTLs, that is cytotoxic lymphocyte, because when they are trained towards a specific antigen, they become cytotoxic because they are trained to kill. So this is what happens. You have this small, big droplet, you have the tumor. We bring the second droplet with the immune cells. They are labeled in green so that you can see or differentiate between cancer cells and immune cells. And then we fuse these two droplets. Okay. And now what we see is something fabulous. What you see is, I'm just showing you one droplet. Remember, we have 234 droplets inside one chip. So you see these immune cells, they're migrating everywhere. Some of them reach to the tumor site and they start destroying the tumor. So this cancer cell starts to die. So this is the dynamics which is happening. So qualitatively, you can tell there are three phases. So in one phase, what you see is that CTLs find this spheroid. Okay, they accumulate on this spheroid, and then the CTLs, the cytotoxic lymphocyte, they destroy the cancer cell. So there are these three phases. Okay, so your CTLs, once they are in the spheroid, they start migrating on this extracellular matrix. Once they start to migrate, some of them reaches to the cancer cells or reaches to the tumor. And then once they reach, they start destroying the cancer cells. Now, using this kind of assay, what we also show that only cancer cells are killed in which case, in the case where CTLs can identify this ovalbumin, this antigen. Okay. We also use the cancer cell types where this antigen is not expressed. And you see that this cytotoxic lymphocyte, they completely bypass this. They don't recognize it, so no killing happens. Okay, so that's something very basic we showed first. Now let's see if the tumor killing or tumor destruction is always a successful process. What you see in this large row or large array of movies, that you have the low number of CTLs in the first row, and you have very high number of CTLs in the last row. And you can see this, that these CTLs, they migrate a lot, and then they destroy the tumor completely when their numbers are very high. But when their numbers are low, they are not able to destroy the cancer cells inside this tumor. So that's very important, that their numbers should be high enough that they can generate an efficient killing. You can quantify these kind of phenomenon where you can identify that whenever you see cancer cells dying, you can label them with this red marker. When they are not dying, you can label them with black, and you identify a range above which, the range of number of CTLs above which they can always kill the cancer cells, below which they never kill, but there is an intermediate range where sometimes the CTLs can kill, sometimes they don't kill. And we thought that this could be an important factor to study, that why sometimes CTLs can kill a tumor and sometimes they can't. And we imagine that it has to do something with the way they can accumulate on the tumor and the way they can kill. So using this large statistics and high resolution imaging, first thing what we can do is to observe when a CTL comes and attaches on the tumor site. What we can also observe is when a CTL leaves a tumor site. And all of this can be quantified over the long time scale, that CTL comes, the number goes up, CTL leaves, their number goes down. And using this kind of statistics, what we have reached to a quantification, which was super interesting. And what you can see here is we can measure the incoming rate of the CTLs on the tumor. You can also measure the outgoing rate of the CTL from the tumor site. And all of this can be measured as a function of number of CTLs already present on the tumor. Okay, so when you have only one CTL present already on the tumor, the probability or the chance or the rate of the next CTL to come is, let's say, 1.5. But when there are already two cells present, the chances of the next one to come is even higher. When there are 3 immune cells already present on the tumor site, the chances of the new one to come is even higher. So that means the more the number of CTLs present on the tumor site, the more the signal to the new CTL to come. And this is something called positive feedback loop. So like imagine some bunch of kids, they find a cake in a party somewhere. Okay, the cake is located in that corner. And then they suddenly start calling all the other guys like, hey, look, we found it, right? So the more number of kids reach to the point, the more shout they, the more noise they make, like, okay, the cake is here. So the new incomers are coming even faster. So this is the process CTLs do in order to accumulate on the tumor site. There are a lot more details into this. I would not go into that. The paper is already out, so you guys can study it further, and you can always throw these questions back to me on my email address, which I will show in the later part of the talk. The way forward, you can use this kind of miniaturized system to take a real patient sample, the patient biopsy sample from the tumor. You can use his own immune cells, and you can train these immune cells, and that's called immunotherapy. And you can study even before introducing these immune cells back to the patient. You can study this in miniaturized systems and see how efficient this immunotherapy would be for the patient. So this kind of system can be used for that. I think I'm short in time. I will take 2 or 3 more minutes, and I will show you the last part of my talk, where I will show a recently invented biomimetic tool which can be used to apply forces on the cells. Now, this is important. I put a very funny image where you know that your cells often come under several range of forces inside the body. To give you some glimpse of it, you have the vasculature, you have the vessels inside your body. The blood is pumped through those vessels at a given pressure. So corresponding to that pressure, your vessels dilate. It can inflate and deflate. So the cells surrounding the vessels, which are the endothelial cells, they can go under stretching. Similar kind of forces come on the muscle, involuntarily or voluntarily. You can stretch your muscle, contract. You have a lot of other forces, even in kind of disease state. I will not go much into detail, but I'm giving you the most common examples. Whenever you swallow something, you have this peristaltic movement of the gut, which happens. Okay, so that's also the place where a lot of mechanical forces come. And these mechanical forces are known to impact cells in different ways. You can have cell spreading, you can have cell death happening due to these mechanical forces. Your stem cells can go under a specific differentiation pathway. Cells can proliferate or not proliferate in response to these mechanical forces. So it's super important for your body to study how these mechanical forces can impact your body or impact the way a tissue performs. Now, to do this, I invented a device. So what the device does is a very simple concept. When you have a bunch of cells, a cluster of cells, I refer them as spheroids. You put them between 2 ceilings and then you press on them. You bring the ceiling down and you press it. And that's how you apply forces in these tissues. The device is under patent filing process, so I can't show you more details, but you use pressure modulation around the device or around the place where you have these spheroids kept, and then you can change the pressure. Corresponding to the changing pressure, the ceiling comes down, and that's how you apply forces. So this is how you can load different spheroids inside this device. And now what you can see is one big spheroid. So you can apply different pressures and you can press this spheroid to different scales. So you can apply different range of forces. What you can also do is to mimic something like muscle, where you can apply cyclic forces. You can press and release, press and release. So this is also something which you can do using this device. Again, this device allows you to do high resolution imaging. In fact, something like this, where you can see one cell nucleus in blue here, cell membranes are marked in this orange, and you can study some responses of different proteins, how they localize, how they spatially change their places in response to these different forces. You can map the location of these cells and see how they change when the forces are being applied to them. And this technology, what it does, it adds a dynamic functional mode into tissues. So I've shown you before the organ on chip platform, but then how you will add a dynamic force module into that. So this is how you can apply forces. And as I told you, in your body, several places the forces are important, and they can completely change the functional way how a tissue behaves. Now it's my last slide. So towards the future, what the field is going towards into is to completely create a human body on chip. So of course you can mimic small organs. Let's say you can mimic a small tumor, you can mimic a small lung, a small muscle cell or muscle cluster. You can mimic even heart, kidney, all these things have been done before. But how you can integrate all of these things into one chip and create a multi-organ or human body on chip. So this is where the field is going towards. Several attempts have been made, but you can imagine that this is it's a complex setup, and it needs much more technological advancement to realize this. And once it is realized, you can imagine that the field will rocket up. It will get a huge boost in order to model different diseases, to do several toxicology tests, and it can even compare the drug responses between different individuals. And that's where people are already talking about personalized medicine. Okay, so the personalized healthcare, so where you can individually test the response of drug. Each individual is different, so the response of the drug could be varying, and these models can really be customized for a individual person in that case. With this, there are so many people who have contributed in this. There are so many people who have contributed in this work. So I would like to thank my labs in Singapore, my labs in Paris, and some of the colleagues who have contributed in this research through their skills of analysis, or through their skills of probably performing some complex biological experiments. And of course, thanks to all these funding agencies. And with this, I would like to invite all the questions which you might have for this talk.
Thank you so much, Dr. Jain. This was an amazing and fascinating talk. I learned so much. So thank you so much.
Thanks.
I think we have time for one question. So one question that we have here is, you've had a really fascinating journey with diverse experiences. Could you please describe your journey to your current position? What led you to the Pasteur Institute, and how has working there helped you develop your work?
Okay, so yes, I can definitely mention something about it, and it's something shocking for you all. So be prepared for it. In fact, the journey was super interesting because I was trained as a mechanical engineer. Okay, so I was trained as a mechanical engineer when I was in my undergrads, and after that I worked in an automotive company. So I was designing steering and suspension systems for heavy trucks. This is what I was doing R&D into. But then I was very interested into microscopic mechanics. So I've always studied this large scale macroscopic mechanics. And that's where my interest into biology came into the highlight, and I started applying for PhD programs. And that's where I got into this Mechanobiology Institute. It's Center of Excellence in National University of Singapore. It's one of the most prominent research center for mechanobiology studies in the world. So that's where I did my PhD work. And after that, I have moved to Paris because I did fundamental research. So where I was studying how cells migrate, how cells apply forces, but I wanted to do now some applied research as well. So to do some applied research, I found this lab in Pasteur, which is very interesting, which works on organ-on-chip platform, where you can recreate or mimic some disease models or some organ models inside the chip. And that's where I started working into it. To tell you, all my mechanical engineering skills, which I acquired since the first day of my undergraduate, are still very much at use. So to give a message to all the undergraduates, or I mean, in fact, all the high school students, never be scared of something which you want to follow passionately. You will always find a way to do something what you love. So that's all I want to say on this part.
Well, thanks, Dr. Jain. That's a really fascinating journey. Another question we have here is, how do you envision applying these technologies on a global scale? And do you hope to apply and implement them worldwide, for example, in developing countries?
So I would say yes and no, because mostly what is happening, so to be very fair, these technologies are first being appreciated and incubated in big pharmas. So of course, I'm talking about more developed side of the world where all the big pharmas exist. So now what they are doing is to rapidly start appreciating these platforms, first to see if they can really scale it up to do different range of drug testing. And I'm pretty sure once this initial scaling up has been already done in the big pharmaceuticals, I don't see a reason why it would not penetrate into developing countries.
That's great. I'll hand it over to Louise for the next question.
So your work combined like mechanical engineering and biological systems, and at the beginning of your career. So how did you envision that you'll be involved with such interdisciplinary work, and what advice would you give to young people that want to incorporate different interests in their career?
Okay, I mean, I think I might have some repetition from the previous answer which I put, but then one thing which I would say to young people, that even though when I was doing mechanical engineering, hardcore mechanical engineering, or even though when I was involved in automotive research, like in heavy trucks and designing suspension systems for that, I was always interested in natural systems, the systems which are thrown up by the nature to solve. The puzzle is thrown up by the nature, puzzle of biology, to see how you can solve it. So I was always reading as a fun part, like even during the breakfast or even while chilling on my laptop screen, I was reading some kind of basic scientific research which is happening in the biological world. And this has really helped me to transition in a very smooth way from a mechanical engineering side to the biological side, because I was well versed or very well aware of what is happening in a broad scale. So if you are interested for something, you have to keep getting your the little pieces. You have to keep getting your little flavors, keep your taste buds active. So that's something important.
Well, it's so amazing and inspiring, Dr. Jain. So another question is, you've described your mechanotherapeutic approach to targeting and treating diseases. Can you please describe this in greater detail, and how do you envision this approach being applied to different diseases and around the world?
Oh, definitely, yes. So in fact, one of the motivation why I started to build this device to apply forces is two research. In fact, couple of research which has been published in last 2 years. It will be amazing for you guys to know that in those research, what they found is when you apply cyclic forces on cancer cells, your cancer cell starts to die. However, your healthy cell doesn't die. And now you can imagine why many people say that, and don't worry, like I can put you some links. I can send it to Meher, and Meher can forward you these links of the research papers. And that's the reason why many people say that when you do exercise, when you stay healthy, when you do a lot of workout, your chances of getting cancer is less, because you are applying a lot of cyclic forces on the body. And recently, high quality research has shown it. So for that reason, I wanted to develop a small device where I can envision by putting small tumors inside and see if I can show what range of forces I can apply to kill the cancer cells more efficiently or something like that. The another aspect of it is something to do with fibrosis. You know, in many disease progression, fibrosis is very important. And during the event of fibrosis, what happens is the mechanical forces, the signature of mechanical forces change, because the more ECM is produced, your cells become stiffer, or your tissue starts to get stiffer. That means it comes under heavy forces. And these high forces completely changes the way the disease progresses. So another reason why I invented this device is where I can apply forces on this, on the cells and tissues. Sorry, oh my God, my phone is always listening me. That's crazy. Okay, so where you can apply forces on tissues and then can study how increased forces can completely change the way disease progresses. So these are few of the directions which I would like to pursue further using this kind of device.
Thanks, Dr. Jain. I think we'll have time for one last question here.
Sure.
So, Dr. Jain, you've worked at a truly global scale with people from so many different countries. So what would you advise to students that are planning to work in another country, and what are some things that they should do and what should they avoid?
Okay, interesting question. I don't have an immediate answer to it on top of my head. But what I would say is like, so when you work in a multicultural environment, something very interesting what you would have in your plate is to learn about different culture. And trust me, the more you indulge yourself learning about different culture, it will parallelly expand the way you think about your research as well. It's beautiful. So I mean, whenever you are in a multicultural environment or a multidisciplinary environment, talk about people, not only about research, but about their culture, about their life, about the way they think about certain issues. And this will definitely expand or stretch your horizons and expand the limit to which you can think about different issues. So this is something I would say. I'm sorry, I don't have any other specific answer to it.
No worries, Dr. Jain. Thank you so much for this amazing and fascinating talk. It was so inspiring and a great conversation. I learned so much, and I'm sure that all the young people here today are really inspired by your incredible work and look at mechanobiology with a new perspective. So thank you so much for opening our eyes to these fascinating processes on a micro scale. And thank you so much for your time today. We really appreciate it.
Thanks a lot for the invitation again. And I'm going to put my email address in the chat. So if you have any specific questions, please feel free to drop me your questions. And even in case you are feeling confused or lost in your career, please don't be shy. I mean, I might be late in responding, but I make sure that if you are in deep waters, if I can pull you out in some way, I would do that. So feel free to contact me. Okay.
Thank you so much.
Thanks a lot again.